Hi, welcome to my talk. My name is Jingna Zeng. Today I'm presenting Investigating the Semantics of Futures in Transactional Memory Systems. This is joint work with Seif Haridi, Shady Issa, Paolo Romano, and Luis Rodrigues. Future is a popular abstraction for parallel programming that allows to exploit hidden parallelism. Several mainstream languages now have support for futures. Let's use an example of Java future to illustrate. Thread A first initiates variable x and y to 1, and then submits a future task, which is executed by thread B. Reads variables x and y and returns the sum of them. In parallel with the future task, thread A sets the value of x and y to 10. Finally, after evaluating the result of the future task, thread A writes the variable t, the sum of z and x. As there's no coordination from the future abstraction between these parallel operations, the final value of z without synchronization could be 11 in the case that x read the initial value and y, on the other hand, observed the updated value 10. The resulting value of z being 11 is an anomaly, which is not possible to be produced in any sequential execution. Although futures gained popularity by allowing writing asynchronous programs in an intuitive fashion, the abstraction itself lacks regulation to concurrent access of shared resources. With this consideration, in this paper, we wanted to introduce a mechanism to regulate concurrent access between tasks executed by the future and the future spawning thread. We pursue this goal by introducing the abstraction of transactional futures. Transactional futures are transactions whose execution is wrapped within futures, and they are spawned and evaluated by other transactions or transactional futures. As a result, we take advantage of transactional memory to regulate concurrent access to shared memory. In the meantime, within transactions boundaries, programmers are able to use futures to coordinate asynchronous computations. Ultimately, in this paper, we study how to combine the notions of futures and transactional memory by encapsulating futures within transactions and allowing them to be submitted and evaluated by other transactions or transactional futures. Since futures are able to generate parallel computations with complex dependencies, which I will elaborate in the following slides, there exist several alternatives for defining the isolation and atomicity semantics of transactional futures, as well as their admissible serialization orders. Consider the basic example of similar read and write operations from the previous slide, but in the context of a top-level transaction submitting a transactional future. Note the task executed by the future's producer up to the point where the future is needed is called the future's continuation. Given the simplicity of this scenario, it is straightforward to determine the set of operations included by the transactional future and the continuation should be executed atomically. It is also intuitive to define the admissible serialization orders. All operations of transactional future should be serialized either before or after the operations of continuation. Think of that. We consider two different semantics regarding the plausible serialization orders of transactional futures and their continuations, namely weakly and strongly ordered transactional future. In either semantic, a future and its continuation should appear as executed atomically. With weakly ordered transactional futures, the future should be serialized either before or after its continuation, whereas strongly ordered transactional futures indicate that the future should be serialized before its continuation. With strongly ordered semantics, the serialization order of a future is defined prior to the future's activation. As a consequence, wherever a strongly ordered future requests to commit, it is immediately possible to determine whether this can be serialized upon its submission. For weakly ordered semantics, on one hand, it provides more flexibility in defining the serialization points of a future. This flexibility comes at a cost. because in order for a future to be serialized upon evaluation, the future's commit request may have to be blocked until the future is actually evaluated. There is another interesting yet challenging scenario where future may escape the transactional context in which they were activated. This is an example of escaping transactional future used as a complementary communication means by two different top-level transactions. In this case, the top-level transaction T1 submits a transactional future TF. In TF's continuation, T1 writes the reference of the future to variable X, reads Y, and commit. And the reference of TF is accessible to the other top-level transaction T2. Comparable to the definition of atomic continuation in the basic example in the previous slide, we use globally atomic continuation to consider all operations included in a chain of causally related events that leads to the evaluation. However, escaping futures can be evaluated after a long period, and it may be undesirable that they may not allow to commit for such a long time. For instance, they could be holding locks for loads of time. This led us to introduce an alternative semantic to ensure that an escaping future is serialized within its spawner. With locally atomic continuation semantic, any top-level transaction during its commit phase is requested to implicitly evaluate any escaping future it spawned. The evaluation is implicit, since it is not requested explicitly by programmers, but is rather imposed by the considered atomicity semantic. To conclude, we have defined semantic models for reconciling the futures abstraction with the transactional memory paradigm. The proposed semantic of transactional futures explore different trade-offs between simplicity and efficiency. There are more details in the extended version of the paper. Welcome to check it out. Thank you.